Now we have seen applications of heat transfer. Now we will discuss how this heat is transferred through various laws. So the laws, those are listed here, as you can see. First law of thermodynamics, second law of thermodynamics, equation of continuity, and equation of flow. So first law of thermodynamics, as we all know, it gives conservation of energy, or what we can say is it is based on law of conservation of energy, as total amount of heat supplied or carried away is equal to total amount of work that is being done on the system or by the system. Then in second law of thermodynamics, it gives direction of heat flow. As we have seen, direction of heat flow is from heat source to heat engine. Then heat engine produces some work and amount of energy is lost to lower temperature thermal energy reservoir. So when we see second law, it gives us the directions how heat is flowing. Then in equation of continuity, it gives conservation of mass, the amount of mass which is flowing in and flowing out from that continuum equation or equation of continuity. We have seen certain laws we have seen that steady flow energy equation. In steady flow energy equation, amount of water which is coming inside the system and amount which is going outside the system is equal, and based on that we have derived something called as steady flow energy equation. And then equation of flow, if you have studied in depth fluid mechanics, you might have come across this Newton's second law of motion and its application called as Navier-Stokes equation. So that Navier-Stokes equation, we are going to discuss it, but not at this stage. So the laws or basic laws are first law of thermodynamics, second law of thermodynamics, equation of continuity, and equation of flow. Then depending on the modes of heat transfer, there are different laws. As you can see on the screen, the rate equation or flow rate equation governs the three modes of heat transfer. First is conduction, second is convection, and third is radiation. So in conduction, the law on which it is based is Fourier law of conduction. We are going to discuss it in detail. Then convection, which is based on Newton's law of cooling. As we all know, the amount of Newton's law of cooling we are very much familiar with. The temperature difference determines the quantity of heat which is flowing. Then radiation, there is other law called Stephen-Boltzmann law. Then these are basic modes of heat transfer, and based on that these are laws. There are certain empirical relations for fluid properties such as specific heat, thermal conductivity, and viscosity. Now you are familiar with the terms specific heat like Cp, Cv, only C we can say. Then thermal conductivity, K, and viscosity, kinematic viscosity, dynamic viscosity, that you came across in your fluid mechanics. So these are certain things that we need to consider. Three modes, which are conduction, convection, and radiation. How heat flows in conduction is through direct contact of molecules with each other and electron flow. In convection, heat is carried by moving fluid. Heat is being supplied to a fluid which is moving. It may be moving due to its density difference because we are supplying heat, or it may be moving because of certain arrangement or forced convection. Then radiation. Radiation is heat flow that does not require any type of media in between. One surface and other surface, heat is being flowed directly without any medium to transfer in the form of radiation or waves, electromagnetic waves. So in practical cases, we do not observe this one say this is conduction, this is convection, this is radiation, nothing else is happening. So it is not like that. It is something which is a mixture of all these things, or at least two things. So in practical cases, it is the combination of one or more cases. And while studying which mode is dominant, or which is having more effect, or at which point there is conduction, at which point there is conduction and convection, at which point there is only convection, that we need to see the application, that we need to see where it is applied, where heat is being transferred, and accordingly we are going to analyze the system. So as you can see on the screen, it discusses in detail conduction. So as we already discussed, conduction is transfer of energy from more energetic particles of a substance to adjacent less energetic particles as a result of interaction between the particles. So particles means here very small part, say you can call it molecules, or even you have studied in your material science, there are certain things which move like lattice structure and all. So as you supply energy to it, it starts vibrating, and when it is vibrating means it is moving. So when it is moving, it transfers the heat from one point to other, or say one molecule to adjacent molecule. So that adjacent molecule also starts moving because of the energy from adjacent one. So as this from molecule to molecule, it goes on transferring the heat. So that is the mode which is called as conduction. Then there is the thing where this conduction happens is in solids. It may happen in liquids and gases also. We have seen this definition in definition of conductions, which is applicable directly to the solids. So what happens in gases and liquids is conduction is due to the collision and diffusion. Collision and diffusion means as molecules starts moving, because it is a fluid, it moves, it collides with the other particles or molecules, and heat is diffused during their random motion, because it is a conduction in gases. Then in solids, it is the combination of vibrations of molecules, as we have discussed in the definition itself, vibrations of molecules in lattice and energy transport of free electrons. Then this thing is how to calculate, how to determine this. So for that we are having certain things called as laws, like conduction. In the last slide also we have seen, here you can see on the screen, conduction is heat flow by direct contact, and it is determined by Fourier law of conduction. So how to go to that Fourier law, that we are going to see here. Here, as heat is being supplied or heat is being transferred, as we all know, it is transferred due to what? Potential difference. So what is potential difference? At certain point it is at higher point, at higher level energy level is high, at certain it is low. So from high to low, it is a natural phenomena. It tries to move from higher potential to lower potential. So this rate of heat conduction through a medium depends on the geometry of medium. So geometry of medium means if it is a plate, the thickness of plate; if it is a ball, then radius of that sphere; if it is a cylinder, then the length of cylinder and radius of cylinder, or something like that. Its geometry, it may include thickness and all, and the material of medium. So of what material that thing is made up of, so that how heat will transfer, it will be determined by that only, as well as the temperature difference across the medium, that is the potential difference. It has to be there, otherwise there will not be any kind of heat transfer. So when we are considering or trying to analyze this conduction, let us consider a steady state. Steady state, you all know, are familiar with steady state. What is steady state? Nothing is moving with time. So consider a steady state condition through a large plane wall of thickness L. So this is thickness of wall is given as L, and its area, cross section area, is given as A. The temperature difference across the wall is delta T. Delta T means it's the temperature difference T2 and T1. At one side of wall there is temperature T1, at the other side of wall there is temperature T2. So from T1 and T2, the temperature difference is delta T. So when this certain arrangement is there and we are trying to study the amount of heat transfer, let us call as Q. So that Q carried through the wall is doubled, it is double as the temperature difference is doubled and area normal to the direction of heat flow is doubled. That means what? We are increasing Q, or what we can say is we will get higher Qs at higher temperature differences and along with higher surface areas, but it is halved we can say, it is half when wall thickness is L is doubled. When we increase the wall thickness it reduces. So something like that, we will see it in the form of equation. Thus here the equation, we are trying to write the equation, the rate of heat product conduction through a plane layer is proportional to the temperature difference across the layer and heat transfer area, but it is inversely proportional to the thickness of layer. This is area which is directly proportional to this rate of heat conduction area, this is temperature difference, and this is thickness. So this is the formula in general form. Let us try to see it in terms of say in mathematical expression. So this is Q, that is conduction heat, which is delta T is temperature difference, A is area, here you can see A, area is here A, this temperature difference is delta T, and this thickness is delta X. Delta X is this thickness of wall, you can see in the diagram itself. And what is this K? K is constant of proportionality, and we call this constant of proportionality as thermal conductivity. Here you can see the equation Q is equal to K T1 minus T2 by delta X, or minus K delta T by delta X, because it is T1 minus T2, it is this thing, final conditions and initial condition. If it is final condition is lesser than initial, it will be negative. Here it could be written as K is a thermal conductivity of material, which is measure of ability of a material to conduct the heat. So it is nothing but ability of a material to conduct the heat. So that is thermal conductivity. You are familiar with this term. In thermodynamics we have seen this thing. As this delta x means what? This thickness of wall. As it is reduced or it is lesser, as delta x tends to 0, the above equation reduces to the differential form. What is that differential form? This delta t will become dt and delta x will become dx. So equation is now Q is equal to minus k dt by dx, and this is called as Fourier's law of heat conduction. So in this Fourier's law of heat conduction, dt by dx is temperature gradient, that is temperature fall or rise. It is gradient, means there is a change, it is not steady. So which is the slope of temperature curve on Tx diagram, the rate of change of T with x. Here you can see temperature is higher, this is temperature at lower. So as we go on from T1 or say from this wall towards this wall, it goes on reducing. So this is called as temperature gradient or change of temperature with respect to